Hello and welcome back. This is a video which will start kind of a new series on neural networks. More specifically, it will be a series on how to build neural networks from scratch, and then maybe we'll look at different stuff. My main goal of this is to build kind of our own library, starting off from a base point, which I'll talk about later or very soon, and then I'll be the goal is to maybe take out the MNIST dataset or MNIST, I'm not sure how to pronounce it, and maybe deploy a model with like a web API. So go from start to finish. The idea is to build the own library, train a model which gets adequate performance, and then deploying it on a web server. What we're going to be doing is getting this JoelNet repo by Joel Gross. He has a nice video, so I recommend definitely checking out the repo. I'll put the link in the description. And this is a repo which kind of gives you a base point for a library. So first, let's start with a very basic introduction of what neural networks are, and then we'll look at the code. In this episode, all I want to do is look at the code, which will be our baseline. I will be modifying the library quite a fair amount because this library is like quite bare bones, but I think it's a good point to start. I don't want to start from basically nothing. Anyway, the idea of a neural network is you have nodes, and this is a fully connected feed-forward model where the nodes, this is the input layer, there can be a number of hidden layers here, and then this is the output layer, right? And obviously this input layer means it's a 3-dimensional input layer. There's a 4-dimensional, one hidden layer, which is 4-dimensional, and a 2-dimensional output. So this network, you say, that takes 3 inputs and then spits out 2 outputs, right? And another way to think about networks is as a composition of these functions, right? So what we can do is look at each layer here. For example, in this case, this would be phi1 and then this phi2. And what we're doing is pretty much traversing through these compositions of functions. And when we go kind of in this direction, right, because this is the first function that's applied, this is called the forward propagation of the network, where we evaluate this feature vector here. So pretty much what we're doing in the forward pass is we take a feature vector and we see what the network predicts. And then when we're training, what we do is we also back propagate or do a backward pass. So we start from the last layer and then kind of go this way through the network to let me just get rid of this, to kind of adjust the weights and the biases within the network. So obviously each connection here is made up of a weight and a bias. This is called a linear layer. So usually what you do is you take this input, so let's call that x0, and you do x0, you multiply this by the weight and then you add a bias. And then as you can kind of do this in batch by using matrices, right? So that's the idea. So the idea is also that each connection has its own weight and bias, and then we can tweak them when we back propagate through a network. Cool. So let's look at the code here. The idea is to just go over the code just step by step. We have this tensor class, which is just simply a renaming of the ND-array class from NumPy, which is quite straightforward. Then I'd like to start maybe with the train, because the train kind of encapsulates the whole library, and then we can kind of navigate to each part. So I'll be changing this for sure, and the idea is to make an API similar to scikit-learn, which is quite a famous library, and then we'll be adapting that. So this training phase takes a number of epochs, and then the epoch loss, I guess, is more to look at the performance of the network over each epoch. But pretty much the idea is that you have this batch iterator, which we'll talk about later. You do forward pass on a batch of inputs, and this gives you like a batch of predicted values. Then what you do is you compute the loss of these, here I guess you add to the epoch loss the loss of these predicted values, but more importantly, you compute the gradient with respect to this batch, and you store it, and then this is actually what updates the network. So maybe let's start that over. What we're doing here, if we look at the diagram, is we take a bunch of feature vectors, and we run them through a network to get like a bunch of predictions, right? And then with these this is the forward pass. And then what we can do with these predictions is with a loss function, what we can do is basically say this. Okay, with this input here, I expected kind of like this output here, right? And now what we do, so let's say this is x1 and then this is like x, right? So what we do is we look at this kind of difference here, the squared loss. So, and we do it for each input. So what we're doing is we're summing the square loss of the batch to figure out how far off we are from the expected value, right? And the idea is that a very high loss means that you're very far away from the result, and a very low loss means you're getting closer. So the whole goal is to minimize the loss, and you do it through gradients, obviously, through calculus. So this is what we're doing. Then what we do with these gradients, the gradients tell you where you can increase the loss, right? So if we take the input and then so if we take, let's say, a point x, and then we take the gradient of this function, right? And then if we look at the loss of this increases the loss. So instead what we can do is we take the negative gradient, and then we also traditionally kind of multiplied by learning rate, which we will see later. And this is the whole idea of adjusting the weights in backpropagation. So this is what's happening. What you're doing here is you do the backpropagation to save the weights, and then here. So here is the backpropagation with respect to the gradients, and then you do the step with the optimizer in that direction, right? And so pretty much for each layer here, you go back and you compute the gradients, and then for each layer here, you do the same. So you do it like kind of in a layer by layer fashion. And this is the whole idea. It's quite straightforward, I guess. And now let's look more in the details. So this iterator comes from this batch iterator class, which is right here. Maybe I'll keep the train here. So this batch iterator class is pretty much, as you might expect, a batch iterator. So the way this works is, maybe it's just read through code, it's quite straightforward. We look at the range from 0 to the actual number of inputs, and then we look at the batch size, and we create like a, maybe if I show you the function, what it does, if we import numpy, and then we look at this function, it's literally just like the range function, just instead in Python, instead it just uses like a numpy array. So this is all it's doing, right? So this is from 0 to 100 in 10 steps, 100 not included. So then you shuffle it if you want to shuffle, usually you do, and then you can construct these mini batches, right? And this is the idea of a mini batch. It's the fact that it's like a middle way from completely a purely stochastic gradient descent, which only looks at one point at a time, and a traditional gradient descent, right? Which is computationally not feasible, obviously, right? Okay, and that's the first bit of the batch iterator. Let's look at forward. By that, let's look at the network. So maybe let's go here. And the neural network is just simply a sequence of layers, as we were discussing here, where each kind of thing is a layer. And then to go forward, all we do is we iterate through the layers. And to go backwards, as I was saying, you iterate through the layers, but reverse. You reverse them first. And this is why Python is quite beautiful language in this sense. Like, it's such a straightforward, readable code, right? And then all you do is you backpropagate the gradients. This is just a helper function to actually, well, we'll see later. But pretty much, let's actually look at the layers and maybe go over some of the math behind them. So, as I said, networks are made of layers, and they're made of two kinds of layers, these linear layers and these activation layers, right? Activation layers are just simply, if we go back to the drawing board, an activation layer is simply one which, well, I mean, there's many kinds, but if this is like -1 and 1, the idea is to, like, it's like a sigmoid function which like squishes them like this. the idea is that for a very high activation, for a very high kind of dot product, I guess, or activation, you want to, it will be close to 1, or else it'll be close to -1, right? And there's many kinds. This is, I guess, just like a sigmoid layer. You can have like a ReLU layer, which looks like this. You can have leaky ReLU, where it kind of drops. There's many different kinds, right? Traditionally, perceptrons were like step functions between 1 and 0. So there's definitely many kinds of layers, and they are. There's like, I guess there's no real theory behind them. I mean, I'm sure there is, but like, no, there's no like best layer. I think more modern layers are usually using leaky ReLU. I think that's like one of the more modern ones. But as far as I know, they all kind of work the same for our purposes, at least. So the idea again is to just switch to squish the output of the linear layer by in a range, so that the numbers don't explode, obviously. Yeah. Cool. So this is what's happening. Now let's look at the actual computations here. And what we're doing in the backward pass is we take the gradient from the layer which is in front of this one, right? So we're going like backward. And then we compute the gradients with respect to the bias, the weights, and then we just return the gradient with respect to the input. And then here there's some calculations, but I think it's worth going over. So for this linear layer, what you're doing is you take this function f of x, where x is like your actual linear layer and f is like the rest of the network. And then what you're doing is you want to compute these gradients, and then we'll go through some dimensional analysis, I guess. So here, what we're doing is we're computing the gradient of y with respect to A, which is this matrix here. And just for convenience, these are the dimensions of them, right? So A is an m by n matrix, x is an n by 1 feature vector. So this means, in this case, this is like n dimensional, right? And this is like m neurons, right? And then this again is m dimensional, right? Because the idea is that well, I guess this is just a vector, this is a vector, and then this is a matrix, right? So obviously the internal dimensions of the matrix have to match, and the dimensions. So this whole product is m by 1, which matches with this, right? Cool. So let's go through it. So here we expect an a dimension. So we're taking with respect to A is m by n. F prime of x is m by 1. X transpose is 1 by n. And as you can see, if you multiply this out, you get n by n. This is why you need this transpose. If this wasn't transposed, it would be an n by 1 vector, which doesn't match. So intuitively, you can think that these transpositions, which are a bit confusing, you just do it to make it match the dimension. Let's look at this. Let's look at all the examples. If x is n by 1, A transpose is n by m. F prime of x is still m by 1. And as you can see, this matches. So because this multiplication is n by 1, and so is the derivative with respect to x. And then again, C is m by 1, f prime of x is m by 1. And this is just an idea of like why you have these transpositions in this order. So obviously this is why in this case you take the left multiplication of this matrix with and you transpose it, or else it just, the dimensionality doesn't check out. So you can expect like these kind of linear algebra calculus to be quite similar to regular like one-dimensional calculus, I guess. Just you have to kind of adjust for dimensions. Obviously there's more of a formal reason, but this is, I think, good enough for this explanation, right? And obviously this comes from the chain rule, because dy dA is the same as dy dx dA. And now dy dx is f prime. Dx dA is, well, this derivative, and if you take it, it's xt transpose. Yeah, cool. And then we do the same. So these are the derivatives with respect to the weight, with respect to the input, which is what we will be back propagating, and with respect to the bias, which so these two will be to actually tweak the parameters. This one is for the back propagation. Cool. We do it the same for the activation layer, like in a similar fashion. In this case, the activation layer is just simply a function instead of like a linear layer. Well, I guess the linear layer is a function too, but this is just more of a general function. And again, we want to calculate since this activation layer has no parameters, you just want to backpropagate it. So you calculate this this partial with respect to the input, which is z, and then you compute it, and by chain rule you just get f prime of x and then g prime of z. And then if we look at the code, this is exactly what's happening. You can see these transpositions and these gradients. In this case, gradient is f prime, right? So as I said, the f is like the result of the kind of already made. So if we're looking at this layer here, f is like this side of the network, right? And so on. So it's like the forward side of that with respect to that layer, if that makes sense. So this is exactly what we're doing. Now we're doing, I mean, I guess Joel is summing, because these are actually coming in batches. And as I said before, we're doing like a middle ground between stochastic gradient descent and then just pure gradient descent. And this is why these batches are here. And then again here, this is like what we were discussing before. And yeah, so it's quite straightforward again, these layers. Let's look at the loss function. Loss function again, you just look at, this is how you compute the loss. Again, we were saying the squared loss, so predicted minus the actual squared. We're summing it because we're looking at multiple inputs, right? Or even at multiple predictions, multiple output layers, right? And then to calculate the gradient, you can just, it turns out to be this, right? Cool. Now let's look at the optimization, which is stochastic gradient descent. Now, maybe a few words about stochastic gradient descent. So ideally, if we have like a loss function here, let's say we have like points here, here, and here. What we can do with stochastic gradient, with regular gradient descent, is we sum all of the losses, or all of like the, not sure how to write it well, but like what we're doing is we are summing through we're using all of the points in our batch, right? But let's say we have like a lot of points and a lot of layers. Obviously this adds up quickly, because let's say we have like 1,000 points, or like, let's say like 1,000,000 points. Is that 1,000,000? That's 100,000. Let's say we have 1,000,000 points. We have to always consider the whole 1,000,000 points. And then let's say we have 50,000 parameters, then we have 50,000 by 1,000,000 points or derivatives to compute, and then that's just for one step, right? So obviously this blows up really quickly. So the idea instead is we could do it with just one point at a time, but then the best middle ground, I guess, is to just take like batches, and that's what we're doing. We split it in batches, and then we kind of do gradient descent on these batches, right? And this is exactly why we have like all these sums and stuff, just to take into account the batches that we need to kind of sum all the batches up and then do that instead. So all this stochastic gradient descent does is it takes the parameters and the gradients of the network, and then we go in the negative direction of this gradient, as I said, because the addition of the gradient points towards a higher loss, so we want a lower loss, and then typically we have a learning rate. Cool. So let's just run it on XOR. If we run it on XOR, we can see this is the left side is like the epoch loss, the right side, or sorry, the epoch number, the right side is like the loss. So you can see the loss is going down and down and down and down and down. And then until you get something which is, so this is like the target value. We want 1 and 0, and then here you can see it's pretty close, right? 0 and 1. Obviously, if you run it for longer, or maybe you have better initialization, it will converge more or less. Or yeah. He also made a fizzbuzz example, which will take a bit longer, but we can let it run. But basically, this is the idea of this This library is quite straightforward, it's quite neat. So we went, I think, over everything. Yeah, I believe we did. Okay, so the idea now is to kind of take this library and improve it a bit. We want to have better optimizers. We want to have different activation functions. More importantly, I want to construct in such a way that it's more similar to scikit-learn. I'm not really a big fan of this train function. I think Joel mentioned it too in the video, but I think this train function should really be a function of the neural net. As you can see, this neural net solved FizzBuzz, which is quite cool. And it worth mentioning that this wasn't trained on numbers from 1 to 100. If we actually look at the code of how this network works, it's trained from 101 to 1024. This is how you construct the layers in this library, and then you can train it, and it's being trained on numbers from 0 to 100, or it's the prediction is on numbers from 0 to 100. So the testing set is not the same as the training set, right? Which is obviously what you would like. So yeah, what I want to do mainly is change this API to make it work a lot more like the API from scikit-learn. Once that's done, I would like to improve it to make it kind of to make it to implement different optimizers, different layers, just to mess around with it, and then we can try to use it on the MNIST dataset. And then ideally at the end, I would like to attack it with some attacks. So that's the whole plan. I hope you enjoyed this video, and if you did, well, I guess I'll see you in the next one. Thank you for watching. Bye bye.